Well, hello everyone, and welcome to another edition of How Bias and Assumptions Kill Science. I'm Rob Stadler, and I'm clearly not Jim Tour. Jim was kind enough to allow me to make this presentation today and the previous one on his channel, and I really appreciate you for that, Jim. And I was actually hoping not to need this video today. You might recall the last time I made a video, I was saying that I hope that this is the end of the series. And with this, folks, I think our discussion, we've had like 5 back and forth videos at this point. I think our discussion has run its course. Unless something revelationary comes up, Dan and Erica, you're welcome to have the last word. Well, unfortunately, some things did come up that need some clarification. I want to make sure people are not misled. And so here we are again. This video is part of a series, and the series started off here with a presentation on my book called The Scientific Approach to Evolution. I don't want to lose the sight of the forest for the trees. We've been focusing on little evidences here and focusing on the trees, but let's not lose sight of the forest. The big point of this book is to say that when studying evolution, we should prioritize data that provides higher levels of confidence, and we should deprioritize evidence that provides only low levels of confidence. And of course, that level of confidence is a spectrum. It's not just black and white, but it makes sense to prioritize the evidence that gives more confidence over the evidence that gives lower. That's what it's all about. But in response to that, Dan Cardinal of CreationMyths channel, and Erica of the GutsickGibbon YouTube channel, and Dave Farina of the Professor Dave Explains channel produced this rebuttal video, which was an hour longer than the video we produce, giving us a lot to rebut in return. So we came back with this video to rebut what they had said. And that led to Erica producing this video, which was an hour longer than what we produced. On top of that, Dan Cardinal produced another video where he did a live demo of how common design doesn't work, according to him. And so we came back from that with a response video where we're basically saying that they're misleading everyone by making bad assumptions, and their bias is driving that, and that leads to bad science. And that's where I was saying that I hope that's the end of the discussion, unless something big comes up.
We've got some creationists who are misrepresenting or misunderstanding, or both, depending on the person in question, a paper.
Well, they went on to produce another 2.5 hours of rebutting that. And there's a lot of misconceptions they stated in there. And so that's why, unfortunately, I have to be back today to produce what I really, really hope is the final discussion on this. Although I hold out not enough hope to believe that's actually going to be the end. So the point of this debate, as it's progressed over time, it has focused increasingly down onto this one particular paper.
The paper is titled Statistical Evidence for Common Ancestry Application to Primates.
This latest rebuttal video says, this paper disproves separate ancestry, and creationists always get it wrong.
Creationists have been going after this paper for years.
That's a pretty strong claim, and so we're going to kind of focus in on that one paper. But again, let's not lose sight of the forest as we focus on this particular tree. And that's an interesting analogy because this figure shows where a lot of this discussion has focused, and it's on a tree versus a forest. So this is comparing 2 hypotheses. One is the tree of life, wherein all of life today came from one common ancestor through the tree of evolution producing all of life, okay? And the other hypothesis, the opposing hypothesis, is that a designer designed life and designed different kinds of life, which after life started then can diversify over time to make little trees. So it's more of a forest instead of a single tree. And in presenting this and considering data between them, I've been saying all along that when Erica and Dan present data in favor of the tree of life, that's their favorite, that they're often throwing in hidden assumptions. And the big hidden assumption that often comes up, or has always come up, is that they assume that the designer of life over here did not reuse parts. So they designed one kind of life and then started over with a clean slate, kind of reinventing the wheel and building the next kind of life. So no correlation structure at the start of life, and therefore modern life, when we look at it today, we sequence the DNA, we see a lot of correlation structure, a lot of nested hierarchy between the different kinds of life. And that is then used to provide strong support for common ancestry.
Common ancestry is strongly supported.
Because of the hidden assumption, the big straw man assumption, that these kinds were designed without any correlation between them. So that caused a big ruckus in the latest rebuttal from Dan and Erica, and that's this rebuttal video here. So again, we're focusing in on this one manuscript. It's called Statistical Evidence for Common Ancestry Application to Primates.
There's this paper that I love, and it's called Statistical Evidence for Common Ancestry Application to Primates.
This manuscript was brought up by Dan and Erica as very convincing evidence that common ancestry, the tree of life, is vastly preferred with infinitesimal p-value.
With infinitesimal p-values.
Over the family separate ancestry or the common design model. And they keep kind of doubling down on this. And this is a very dramatic, strong claim here that this paper disproves separate ancestry. And so we need to dig into that and see more of what's actually going on here. So I'm going to start off, maybe this will surprise everyone, but I'm going to start off by actually making a concession here. When I speak of the forest of life, and you just saw all of this here, and I make the statement, no correlation structure at the start of life. Well, I know it turns out that in the paper by David Baum, which we just showed, the statistical ancestry paper, he did not literally derive the DNA at the start of life. So he didn't actually try to derive exactly what the DNA was in each of these kinds at the start of life. I get that. But if we want to get into the details and get more technical and more accurate, you could say, about that statement, let's get into that. And right now, I'm just going to give a little thumbnail overview of some of the details of this paper, and then we're going to go a little deeper. So I want to start by just giving an overview. So what they did in the paper is they randomly generate DNA for each family. So they literally take a random number generator and make up DNA for each of the families. And then from each set of that DNA, so one DNA for each family, so it's like a matrix of families and DNA code. For each matrix they generate, they derive the most parsimonious phylogenetic tree, which is a way of trying to connect these families together as if there was common ancestry. And they do that 1,000 times to arrive at a distribution of the type of correlation structure that could have arisen by chance alone. So they're trying to see what chance alone could provide as far as a nested hierarchy between the different families. And we'll get into that more. I know this is kind of technically challenging. Then here comes the big straw man assumption. Then they assume that under this common designer model, the designer of life would not have provided any more correlation structure between families than could be provided by chance alone. And that's the big key assumption we're going to be focusing on. So in other words, they assume negligible, not zero, but really, really close approximation to zero, negligible correlation structure between the families. And that happens to imply, when you think about it, that happens to imply that there's negligible correlation structure at the start of life, even though they didn't literally find the DNA or use DNA at the beginning of life. So basically, it sums up, they basically assume there's no correlation structure at the start of life, which is my statement here. So if I want to be more accurate, this original statement that I made, and I've made it many times, I could have made it slightly more accurate, but much less understandable if I had changed these words here. Instead of no correlation structure at the start of life, I could have said, the designer provided no more correlation structure between families than chance alone would have provided. That's more accurate, but a lot less understandable. And so that's why I went with this one. The second statement here, that therefore observing a correlation structure in existing life, in real DNA from real living things, it strongly infers common ancestry because of that hidden assumption, and that's a straw man argument. That statement is untouched. I totally stand behind that. Nothing changed there. And this is a straw man argument, and let's go into some details to explain that better.
If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together, and I will share with you about why I embrace the resurrection of Jesus.
The prediction is this: neither Dr. Tor nor Dr. Stadler will display an understanding of the methods in that paper.
The Baum et al. Paper, this is that statistical ancestry paper. We go into the methods now. We're going to have to dive deep into the methods. So this statement, to evaluate whether the observed hierarchical signal is more than expected under species or family separate ancestry. We're only interested here in family separate ancestry, so forget the species part here. But whether the observed hierarchical signal is more than expected under family separate ancestry, we use the PTP test. And that's the permutation tail probability test. It's a statistical test. It's related to the t-test. Hopefully people are familiar with t-tests in statistics. It's a pretty simple test. And they reference this paper that explains this PTP test very clearly, very nicely. I have no problems with this test. I think it's a neat idea. It makes sense. But the title they choose is very interesting and very helpful. So they say, could a cladogram, so think of this as your phylogenetic tree, could a phylogenetic tree this short have arisen by chance alone? Okay, so when you build a phylogenetic tree from something like genetic data from DNA, if there's a lot of nested hierarchy, if there's a lot of correlation structure between the DNA, you end up with a short phylogenetic tree. So the more correlation you have, the shorter the tree, because you have lesser mutations needed, lesser changes to try to explain. And so they developed this test to try to help people to know that when I develop a phylogenetic tree, can I have confidence that I'm actually seeing significant correlation here? Or is it just something that noise alone, that a random process could have generated? So the point of this PTP test is to distinguish phylogenetic trees that actually have significant correlation structure from those that are just no different than noise, no different than random. So it's a pretty low bar kind of test, just to say that you stand apart from what chance alone could have produced. So let's go into that a little deeper here. These are the 5 steps of the PTP test. And again, I have no problems with this. I think it's a neat, innovative way to do things. So first, you produce random DNA sequences for the set of life forms that you're interested in. Then you derive the most parsimonious phylogenetic tree for that data. And it's weird to think you try to derive a parsimonious phylogenetic tree for random data. It's kind of weird, but that's what you do because you want to characterize what chance alone could accomplish. And this tree that you derive is going to be quite long because there's lots of required mutations to explain how all of this could have come about from a common ancestor. It's going to be a long tree. And then you plot out the tree lengths then, and you do it, you plot out a tree length, you do it again, and they do it about 1,000 times, could be 10,000, doesn't really matter. The point is you get a distribution of the tree lengths that you come up with. And it's like a histogram. These are all the different tree lengths that I came up with for 1,000 permutations. This is just a cartoon, and I'm drawing a cartoon. This isn't real data. So just so you know, I'm just trying to explain it. Then you've done that. You understand what chance alone could provide as far as tree lengths. Now you take the real DNA data that you take from real living organisms, and you derive the most parsimonious tree that you can derive from the real data. And if the results, the length of the phylogenetic tree that you come up with from the real data, if that tree length is significantly shorter than the distribution that chance alone could provide, then you can say, aha, I'm certain that my phylogenetic tree, that my data has more hierarchical structure than could be produced by chance alone. So my tree is not just random noise. That's the point of the test. The statistical comparison is a lot like a one-sample t-test, where you're comparing a distribution against a fixed value. And that's how this works. And again, I have no problems with this. I like it. It's terrific. The problem is people often misinterpret it. So if you see that real data stands apart from what chance alone could generate, Dan and Erica call this strong evidence for common ancestry.
So that is strong evidence for common ancestry, because
That's a misinterpretation. That is having applied assumption on top of the result. What this result actually shows, which is very clear, very scientific, is that your true DNA data, the phylogenetic tree you derive from it, it has nested hierarchy, it has correlation structure that is statistically significant, better than what chance alone could provide. So what you have shown is that you have hierarchical structure. Dan and Erica assume then that that means you have strong evidence of common ancestry. But there are other things that could produce hierarchical structure, such as a common designer. So they're assuming away the common designer when they make this statement. Well, watch out for your assumptions.
Because of you, millions of people have heard the gospel. If you confess with your mouth Jesus is Lord and believe in your heart that he's risen from the dead, and you will be saved. That's right. That's the requirement. We talk about science concepts which draw people in. Take these nanomachines and have them drill into cells. This would be a great way to kill cancer, right? We also talk about Jesus Christ, who's the best in everything.
My faith in Jesus Christ means more to me than anything.
If you could continue to give or give for the first time, we would certainly appreciate it. You can go to jesusandscience.org/donate. All U.S. donations are tax deductible. Thank you so much.
Okay, now the Baum et al. Paper takes the big leap here of applying the PTP test to test separate ancestry, to test if the common designer is possible. And that's where things start to go awry. So again, we go to this statement in the methods to evaluate whether the observed hierarchical signal in real DNA is more than expected under family separate ancestry. We use the PTP test. So this is application of the PTP test to a place that it hasn't been applied before, and in a method it hasn't been applied before. But when you read the sentence, and I highlighted here more than expected, hopefully you're asking yourself, well, what hierarchical signal is expected, right? That's where the key assumption of the paper is. And unfortunately, it's not clearly stated in the paper. It's in there, but you have to really read it and think about it. So what hierarchical signal is expected by these authors under separate ancestry? The answer is no hierarchy of any statistical significance. In other words, the designer who designed these separate families could not have put more hierarchical structure, could not have put more correlation between the families than chance alone would have produced. Okay, that is the big straw man assumption. And I've been saying all along the paper has straw man assumption, but now we're going deeper. We're peeling back the onion and going deep into the layers here to show where the straw man assumption is here. And this was all provoked, of course, by Dan and Erica having peeled back the onion to claim that I was wrong all the way through. So I had to go through all this also. So again, keep in mind that the purpose of this PTP test is to detect any hierarchical structure that is greater, statistically greater than noise, greater than what chance alone would have provided. And that's written in the title. Very clearly, that's the purpose of this test. So when applying it to separate ancestry, they apply this huge straw man assumption, and that's how they get their results. So let's look at that. So we've already gone through the steps of the PTP test. Those are grayed out here. But what they do in this Baum paper is add number 4. So steps 1, 2, and 3, they create this distribution of tree lengths of what chance alone could have provided. Then the big assumption, step number 4, assume that if separate ancestry is true, right? Assume that if that forest of life is true, then the actual DNA that you collect from modern life would have produced tree lengths that fit within this distribution, right? Because the designer is not allowed to provide any more correlation structure than chance alone would have provided. So in other words, when they get the real DNA and find the tree length the most parsimonious tree to explain the real life DNA, if it fits under or within this distribution, that would say evidence of common design. That's what they're saying. But of course, when they get the actual data and they actually do the phylogenetic tree, it comes out to be over here. This has more correlation structure than they're assuming is possible from a designer. And therefore, they end up with a very, 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 very small p-value.
With infinitesimal p-values.
Meaning this is very statistically different than this chance alone distribution. I hope that gives you a good feel for the kind of assumption that they're making here. So now we get to Dan's argument of why this PTP test is justified in being applied to separate ancestry. And Dan here expresses a lot of confusion. We're going to go through some clips. And it's hard to go through this because there's a lot of confusion expressed by Dan. I'm going to show some clips. The big point is that Dan seems to think that by doing this 1,000 repeats in deriving phylogenetic trees from random data, he seems to think that that covers all possibilities, all possible phylogenetic trees, all possible correlation structures. And so he thinks that it's providing the best case scenario for family separate ancestry. It's giving it the best opportunity possible.
The key thing here is that the authors are not assuming the absence of a pattern among the separately created trees. By randomly sampling from all available phylogenetic trees, they determined the best case scenario in terms of tree length without having to specifically characterize what the starting states would look like.
So you heard him say that by randomly sampling all possible scenarios, that they're giving the best case scenario for family ancestry. Keep that in mind, please.
They're probabilistically determining what that optimal starting state would be.
So he thinks this test is giving the best possible scenario for family separate ancestry. That's a major misunderstanding, Dan. And we're going to talk through that. We're going to explain it. But what they're doing is they're probabilistically determining what chance alone is likely to produce, which is essentially the same as an absence of pattern between the families. And that allows for any real hierarchy actually seen in the DNA to be detected.
Right? They're trying to find the shortest trees. They're going to have the optimal starting states. That's the point of the methodology, is to do what Rob is saying they didn't do.
Okay, and the reality here is that Dan's got that completely backwards, that they are not showing the best case scenario. They're not testing every possible scenario. I'm going to try to explain, I think, where Dan's misunderstanding comes from. And in this clip, Dan is talking through the paper about the PTP test.
So we're going to go down here, the cladistic permutation tail probability, and I want to highlight this line. The observed tree length is compared to a standard defined by the theoretical minimum number of steps possible with the data, right? You randomize your data, so you're getting every possible configuration of those same data, right? You're preserving the frequency of ancestral and derived traits, but you're randomizing the allocation. What do the best possible trees look like? And I want you all to put a pin in that line, right? Because we're not just comparing random trees, we're comparing the best possible trees to our actual distribution, right? That's a key point that we're going to come back to later. So everyone just remember that line right here. Okay.
Write that down. Write that down.
Write that down.
Dan wants us to put a pin in this line. Please notice that this line that he has highlighted and that he's talked through, and he says that this line tells us that they're getting every possible combination from this data, and the best possible trees come from it. The major misunderstanding Dan has here is that this section of the paper, if you go back just one sentence, you go to the beginning of this paragraph, in this paper, they're talking about some different metric of the quality of a phylogenetic tree. This is called the consistency index. And this is a metric of the quality of a phylogenetic tree that's been around for a while. And in the paper they wrote about the PTP test, they're giving a little historical background. They're saying there's also this thing called the consistency index, And they're basically saying that it has some limitation, that the consistency index has some issues, and that's why they came up with the PTP test. So Dan is drawing conclusions and referring to something that's only about the consistency index, which has nothing to do with the PTP test. And he's misunderstanding that and drawing the wrong conclusions based on the wrong metric, and that's a shame. So that's why Dan is confused, I think, and that's why Dan thinks that this PTP test is providing the best case scenario, and it's considering all possible configurations. Now, I need to go into probability a little bit to give you a feeling for why this PTP test is not testing all possible configurations. So in the BOM paper, this is the paper we've been struggling through, this table 2 contains the key result when they're testing for family separate ancestry. And yes, I know, Dan, that there are other rows here from other data sets. Please don't call me a liar and make a 2.5-hour video about why I'm a liar, because I didn't include the other rows from this table. So we're talking about the Perlman data. This shows that when they talk about using the PTP test, they're considering 16 families, and in each family, they're considering DNA of length 34,860 nucleotides. So when we say that they randomly generated DNA as part of the PTP test to derive this distribution down here, they did 1,000 draws of 16 times 34,860 random DNA nucleotides. That's how the test was run. So let's do just a little bit of math here. Each nucleotide has 4 states. Could be an A, a C, a T, or a G. So they're talking about a distribution that has 4 different states raised to the power of 16 times 34,860. To try to put that into more convenient terminology, that would be a number 1 followed by 335,804 zeros. That's how many possible random draws from this data you can have. This is an incomprehensible number. It's just impossible to understand that. Let me try to put it in perspective. If you took every computer on the planet Earth, every computer, and you set them to one task, which is to generate randomly this 16 times 34,860, and you allowed those computers to run for 14 billion years, even 100 billion years, you would not even come close to beginning to test every possible permutation, every possible configuration. By doing this Monte Carlo simulation and just drawing 1,000 samples, 10 to the 3, not 10 to the 335,000, what they're trying to do is get a feel for the distribution of what chance alone could produce, to get a mean value and a standard deviation so that they can apply a normal Gaussian distribution to this and get a feel for what chance alone could produce. And in that case, it's a very tight distribution, and genomes with almost no hierarchical structure are going to vastly predominate. Genomes with any degree of hierarchy or correlation are what I call here impossibly rare, basically zero, near zero. You're not going to see them. It certainly does not in any way provide the best case scenario for family separate ancestry. Again, all the test is trying to do is show that you have hierarchical structure that is statistically greater than noise or chance alone could produce. And that's what they're doing here. So to draw this to a conclusion, Dan and Erica and this Baum et al. Paper from 2016 adopt a huge hidden straw man assumption, and that is that the nested hierarchical structure expected under separate ancestry, expected by a common designer, is close to zero. It's no more than what chance alone could have produced. So they're saying that the designer of life could not reuse parts between different families, or at least could not reuse parts to the degree that it could be detected as being greater than a noise signal. And so the observation in real DNA from true living things that has a strong nested hierarchy, a strong correlation between different families, that is very wrongly interpreted as strong evidence of common ancestry, all because of this straw man assumption that they make. And so the point is that bias and assumptions are killing good science. Now, sadly, Dan and Erica doubled down on this wrong conclusion in their latest 2.5-hour tirade with various put downs and trying to make me look bad. And it's a very wrong conclusion. And they say that creationists always get it wrong.
Hello, everyone, and welcome back to Creation Myths.
It's also interesting to note that Dan did a little bit of theatrics here, that Dan came up with a video preceding this one where he said, I'm going to predict what they're going to say.
I'm going to put myself out here and make a public prediction before that video from Dr. Stadler and Tor comes out.
And then when we released the preceding video to this one, he said, oh, I nailed it. I got them.
And I nailed both of them almost to the word.
And it turns out that, as I showed here, that he was wrong the entire time. And he basically predicted that we were going to get it right, and we got it right. And so the conclusion of our prior video completely stands untouched in my mind, that they are misleading everyone. Their audiences have been misled. And this is in part because of their bias. It's in part because of bad assumptions and straw man assumptions that they have accepted. And it's also in part because I don't think they really understand the statistics and the probability. So Dan, before you make a 2.5-hour rebuttal video to this, I really implore you to consult with a statistician and get this cleared up and get this straight so that we don't have to spend a lot of time on this. And so folks, I really want to thank you for your time and bearing with this and going through this with me. I ask you to caution yourself and don't be fooled. Don't be fooled by what these people are saying. And in the end, I give glory to God, and I'm grateful for this opportunity to be here and to present this. And God bless you. Thank you.
Thank you for joining me today. If you could give us a like, share, or podcast review, we would appreciate it. If you have any questions, you could send them to ask@jesusandscience.org, and we'll try to answer some of those questions in an upcoming video. And if you do not believe in the physical resurrection of Jesus Christ, and you want to hear about why I believe, send me an email to tour@drjamestour.org, and we'll get together by Zoom, and I'll share with you why I embrace the resurrection of Jesus Christ.